In section 1.3, we're going to take a look at complex numbers. In your previous math courses, probably the majority of the work that you've done, if not all of the work that you've done, has involved the real number set. Complex numbers are a larger set of numbers that contains the real numbers, but that also follow rules that real numbers do not. For example, we'll start with the imaginary unit I, defined as the principal square root of the number -1. Within the set of real numbers, the square root of a negative quantity doesn't exist. But here in the complex number set, that number does exist, and we label it as the imaginary unit I. Because I is equal to the principal square root of -1, squaring I would yield -1 as a result. These two quantities are going to be very important for you to know very well. I is equal to the square root of -1, and I squared is equal to -1. A complex number is a number of the form a plus b times I, where a and b are real numbers and I is the imaginary unit. The number a is said to be the real part, and the number b is said to be the imaginary part of the complex number a plus bi. To add and subtract complex numbers, we simply have to pair up the real parts of the numbers and pair up the imaginary parts of the numbers and add or subtract as indicated. It's similar to collecting like terms. Let's look at an example below. The complex number 6 minus the square root of -64 is to be added to the complex number 4 plus the square root of -9. We're going to start by writing these square roots as imaginary units. So the first number is really 6 minus 8i, and the second complex number is really 4 plus 3i. Now we're going to combine the real parts, 6 plus 4, and we're going to combine the imaginary parts, -8i and +3i. So the sum of these two complex numbers will be 10, and then -8i plus 3i will give us a -5i. This is the sum of the above two complex numbers. The sum itself is a complex number with a real part of 10 and an imaginary part of -5. In our second example, we are going to subtract two complex numbers. Again, we combine the real parts and combine the imaginary parts. So in this case, we have 14 minus 3 as the real part, and then we're going to add that to 9i minus 3i. Let's pause here a moment. We are adding, but in essence, we addressed the subtraction because we are subtracting 3 in the first part, and we are subtracting a 3i in the second part. That means that every subtraction can be rewritten as an addition as long as we properly address the subtraction within the real part and the imaginary parts. 14 minus 3 is 11, and then 9i minus 3i gives us a +6i. So note that the result of subtracting two complex numbers is itself a complex number. In this case, the real part is 11 and the imaginary part is 6. To multiply complex numbers, we are going to distribute similarly to how we would distribute when multiplying binomials. In the following example, we have the complex number 6 plus the square root of 5 quantity squared. This is not a complex number actually. This is a real number that's being squared. Perhaps it's here as an example so that we can draw some similarities as we look at example 2. Let's recall how to properly distribute. 6 plus the square root of 5 when squared just has the same factor appearing a second time. You might recall the FOIL acronym when distributing in multiplying two binomials. The F in FOIL stands for first times first. The O stands for out times out. the I for in times in, and L for last times last. So let's look at these four smaller products. 6 times 6 is 36. 6 times the square root of 5 is 6 square root of 5. Square root of 5 times 6 will give us another 6 square root of 5. And finally, the square root of 5 times the square root of 5 will give us 5. By combining like terms, we have that 36 plus 5 is 41. And we have that 6 square root of 5 plus another 6 square root of 5 is equal to 12 square root of 5. Notice that the result of this multiplication gives us a real number written as the binomial 41 plus 12 times the square root of 5. Now let's repeat the process, but in this case, the second example does include two complex numbers that are being multiplied together. Just like we did in example 1, we are going to distribute using that FOIL acronym to make sure we do so properly. First times first will give us negative 4 times 5, which is a negative 20. Out times out gives us a negative 4 times a negative 6i, which is a positive 24i. In times in will give us a negative 3i times 5, which is a negative 15i. And finally, last times last gives us a negative 3i multiplied by a negative 6i, which is 18i squared. Now, let's simplify. We can collect like terms. 24i and negative 15i becomes positive 9i. There's another thing that we could do here to simplify. Recall that I squared is equivalent to negative 1. That means that this last term is really 18 multiplied by negative 1, or negative 18. That means that we have another pair of terms that are like terms. Negative 20 and negative 18 can be combined to become a negative 38. And so our final product, our final answer, is a complex number. The real part is negative 38, and the imaginary part is positive 9. Finally, to divide by a complex number, we have to review the concept of a complex conjugate. A complex conjugate of a complex number involves the same real part, but the opposite sign for the imaginary part. So for example, a plus bi and a minus bi would be complex conjugates. Conjugates are used when we divide by a complex number. In essence, we multiply the numerator and the denominator by 1 in a creative way using the complex conjugate of the denominator. Remember that we don't want to change the value of the quantity, so multiplying by 1 will preserve the original value by changing the format. Let's look at the following example. We have 2 minus 3i divided by 5 plus 7i. This is in really small print, so I'm going to rewrite it so that we can work with it a little bit more easily. So no changes as of yet. We're going to multiply this quantity by 1, and we're going to do so in a creative way. Multiplying by 1 is going to involve multiplying by the conjugate of that denominator. So notice that we have opposite signs here. Originally we had addition. Here in the complex conjugate we're going to have subtraction. But because we don't want to change the value of our quantity, we want to multiply the numerator by the same amount. In essence, we are multiplying by 1 in a creative way. Now, let's carefully distribute the numerator where we have multiplication and the denominator where we have multiplication. In the numerator, first times first is 2 times 5, which is 10. Out times out is 2 times negative 7i, which is negative 14i. In times in is a negative 3i times 5, which is a negative 15i. And last times last is negative 3i times negative 7i, which is positive 21i squared. We will simplify in just a moment, but let's go ahead and distribute in the denominator as well. First times first is 5 times 5, or 25. Out times out is 5 times negative 7i, which is negative 35i. In times in is 7i times 5, which is a positive 35i. And last times last is a negative 49i squared. Now something interesting happened here, and it was not due to a coincidence. In fact, this is by design. Note that these two middle products are opposites of each other and they add up to 0. Negative 35i plus 35i will be 0. Also note that we have I squared again, which is equal to negative 1. That means that our last term in the denominator is a negative 49 times a negative 1, or a positive 49. Let's go ahead and simplify as much as possible. In the numerator, we have negative 14i and negative 15i as like terms, so they can combine into a negative 29i. Again, we have an I squared, which is equal to negative 1. So 21 times the negative 1 is going to give us a negative 21 as our last term. If we combine the 10 with the negative 21, we get 10 minus 21 is negative 11. So that will become the real part. In the denominator, we have 25 plus 49, and so that essentially will give us 74. Let me change to the correct color so that we match. Although this is an acceptable final answer, it's preferred that we write our answer in the form of a complex number. So we will have a real part and we will have an imaginary part. The real part will be negative 11 divided by 74, and the imaginary part will be negative 29 divided by 74, and of course we multiply by the imaginary unit I. This is the preferred way to leave the quotient because it is written as a complex number, a plus bi, or in this case, a minus bi. When you're working in my math lab, the system will insist that the answer be written in this format.